Welcome to lecture 28 on risk management and insurance. In this lecture, we introduce the Black-Scholes option pricing model. But first, I would like to repeat something from last lecture. In last lecture, I mentioned arithmetic, stochastic processes, and geometric processes. Let's make sure that we all understand what the difference is. Now, in an arithmetic process, you have here the change in the variable, maybe the change in the price of an asset, so that's a dollar change. And the drift here is also directly defined in terms of dollars. And the same thing here for the scaling factor of the standard deviation of the Wiener process. That's also given in dollars. That's an arithmetic process. It's sometimes called a random walk with drift. Now, with the geometric Brownian motion, here the drift we define as a percentage of the level of x. And also the standard deviation, the scaling factor for the standard deviation, we define as a percentage of the level of the variable. So the x appears here and here. And then here we have the change in the value of x, which may be an asset price. So here the geometric process, A is a percentage. So maybe 5% of the level of that variable. So we get here dollars again, 5% of the current value of the variable. Then again, you have your dollars naturally. And here also, you have here the scaling factor is a percentage, maybe 30% of here the value of the asset. So that then also gives you dollar. So in the end here, again, we have the dollar change in the value of the asset. Now, both types of stochastic processes are important in finance and also in science and engineering, arithmetic ones and the geometric ones, they both occur. And I must say, the terminology is not absolutely certain. Sometimes people, or even in writings, the things get confused and they call it wrongly. So you have to be careful here what people really mean. But it's a basic difference between a geometric process and an arithmetic one. It's an important difference. Now, the logarithm of a share price, that's where we stopped last time. The logarithm of the share price follows an arithmetic process. Let's go back to that. So we had here, let's say it's a share price, and then we take the logarithm of it. So how does the logarithm of the share price behave? So the G function is just a logarithmic function here. And what we got here is this here, equation 14. You see the G is not on the right side here. The G is not here. Well, that's now an arithmetic process. The G is a change in the logarithm of the share price. That's a percentage change. And so the drift here directly is a percentage change. The mu is the drift in the share price, and then we have to correct a bit for this small term. But mu basically is the change, the rate of change in the share price in a time period, maybe 5% or 7% up. And here's a standard deviation. It's also the percentage measured in percent. And so we get here the change of the share price in percent. So that's why the semi-logarithmic graph works. We said it gives you true representations of percentages, of changes in percentages. And it's an arithmetic process. So it's no longer exponential. So taking the logarithm in the semi-logarithmic graph actually change the graph from exponential to linear. It becomes an arithmetic process. So here you have the mathematics for it. So that the semi-logarithmic graphs make sense. So the logarithm of the stock price follows an arithmetic process. And we can use this. Here's the change in the logarithm. dg, that's a change in the logarithm of share price from time small t up to time big T in some interval. And here it's just the growth rate that we have here measured in percent. And basically you can neglect this, that's a small term. And if you have 1 year, you multiply by 1. And if you have 2 years, you multiply by 2 here. Okay, so then naturally, then you get this rate of return twice. And same thing here, here I have the variance. Usually here we plot, we write the standard deviation, but in the books I write here now the variance. And also the variance is directly linear dependent on time. If 1 year you go to 2 years, 3 years, naturally the variance of the return will get bigger. So expected return may get bigger, but it also will become more uncertain. Okay, so the variance directly matters, time directly matters here. And we have the normal distribution here. So that stands for the normal distribution. So the percentage change in the share price from small t to big T in that interval has a normal distribution, and that's the expected value of this percentage change, just a mu if it's 1 year, and if it's 2 years, then it's twice this mu. And you may forget about that. And here you have the variance, which also is directly linear to time. The variance will be twice if the time interval is twice as long. But then, because this is a constant, the share price at time small t today is a constant that's given. So you can actually just add this in here. You can subtract it here, you can add it here. So that's what I have done here. I subtracted it here and I added it in here. So the logarithm of the future share price at time big T is initial price in logarithm plus this percentage change, this expected percentage change. And here's a variance, okay, no change. And if you would like to have it per time period, yes, then you just have to divide by the time period. So if you want to have it per year, if it's 1 year, that's then divide by 1. But if it's 2 years, then you divide this by 2. So here it drops out. So it's no longer here. And sorry, I went back to up here. So here it drops out. And here, be careful, that's a variance. So you have to divide by t minus t squared. And then you have it on top and below. So t minus t squared, one bracket cancels out, and you have t minus t down here. So you must divide it by t minus t squared because it's a variance. And then t minus t cancels out against one of the t minus t down here. And you just have the other one left over here. Okay, that's something I have directly out of the Hull book. I kept it here a little bit short. So if you really want to work with that, then naturally you should read it in the Hull book. Let's make an example. So let's have the share price today at time small t is $20. The drift, the annual drift is 8%. The volatility is 30%. Now, what is the probability distribution of the share price in 3 months? And I directly plug into equation 17. So $20. You see, it's a natural logarithm. Now you take from the $20. Then we have here the 80%, as 8%, 0.08. Here we have the variance. So takes the square of the standard deviation, 0.3 squared, and so on. You see here is the $20, the natural logarithm of it, so it's 8%, and here's a standard deviation squared. It's a variance. So volatility usually isn't given as a standard deviation. So when you need the variance, you have to square it. So it's squared here. And so plug in everything. And so actually here we get the logarithm of the share price in 3-month times with this variance here. And it's normally distributed. Now, the 95% confidence intervals, if you have the normal distribution, that's naturally plus minus 2 times the standard deviation. So exactly 1.96, but roughly 2 and roughly 2. So that's what you have from the tables of the normal distribution. Here now I need the standard deviation. So that's a variance, remember, that's a variance. So I have now here to take the root. Okay, so here a lot of opportunities to make silly mistakes. So be careful. So here it's a standard deviation. So here we need now the 95% confidence interval is roughly plus minus 2 standard deviation. So here we now work with the standard deviation. So 3 minus this and 3 plus this, okay? That gives a 95% confidence interval, but that's now for the logarithm, and we would like to know the non-logarithmic figures. So take the logarithm out, takes the anti-log, and that's how you do it. You probably know that. Take e to the power, and then you get the non-logarithmic confidence interval, 95% confidence interval. So with 95% chance, the share price will be between 15 and 27. And that's naturally very useful information. Now, if you have difficulties to go from here to here, maybe that you have not seen before. Now, then just goes the other way around. Go from the bottom line here to the upper line, and just takes a logarithm here. You get the logarithm. It also takes a logarithm here. This just brings you down to power. So we just have down to power. So taking the logarithm, here's a logarithm of the e number, it just the power comes down. So maybe it's a little bit easy to see to go from this line to that line. Okay, so we have here a 95% confidence interval, and so with this information, you have a share, you buy a share for $20. You know the drift is 8% per year. That's naturally historical data. And then the volatility maybe 30% over the past few years. So you use that. If those parameters do not change, then the 95% confidence interval of the share price will be like that. Now you can do, what we really do here is a log normal distribution. For the log normal distribution, those two equations hold. The expected value is like this. You have here the current share price at time small t, and then that's the expected price at time big T. So that's easy to see. You have initial share price, and it just grows at mu. And the variance you have here. So that's harder to derive. That really needs some more advanced knowledge of mathematical statistics. Now, when we plug in the data here, we get now an expected share price of $20.40. The expected value is $20.40. It's actually closer to the 15 than to the 27. So the expected value is not in the middle, but that's because, okay, here's a logarithm matters. And the variance will be 9, and the standard deviation will be 3. So plus minus 2 standard deviation, yes, that brings you roughly up to 26, 27, and down here to the actually below 15. So you get here a somewhat different answer if you do it this way. Now, if you really work with those things, you have to read about this in the whole book. Okay, what exactly is the reason? We get something similar here, but not exactly equal to what we had on the preceding page. Now let's go to option pricing. And let's assume stock price, share price follows a geometric Brownian motion. It's a very popular model, the geometric Brownian motion for share prices, because this has to do actually with efficient market hypothesis. That share prices follows those unrelated shocks over time, this Wiener process, plus maybe a drift, a deterministic drift. That's closely related that the financial markets are efficient. Then share prices should follow this geometric Brownian motion, or at least closely to the geometric Brownian motion. Now the Ito lemma then tells you what is the stochastic process of some derivative. The derivative could be an option, or the derivative could be a forward contract. I use now here the letter small f for the derivative, no longer the g, and also not the and also not the x. So Ito equation just directly tells you that is now the stochastic process of the derivative. There is a new drift, there is a new volatility, but the shock is the same. So if you have a strongly positive shock here to the underlying share, then the derivative is exposed to the same strong positive shock. So remember, the derivative is just some function of the underlying share. We can use this functional form, and then the Ito equation gives me, okay, the behavior of f over time. So it's important here, we have this shock, it's the same shock in each period. And what you see here, the volatility of the derivative is this ratio times the volatility of the underlying asset. Here we have sigma s, and here we have sigma s times this ratio. This ratio measures the sensitivity of the price of the value of the derivative with regard to changes in the asset price, underlying asset price. So that's a partial derivative here. So that's why I write it down like this. You see we have this function. So this here is the first derivative of this function with regard to s. It's a partial derivative. So the volatility of the share price is this, sigma s times s. The volatility of the derivative is here the old volatility of the underlying share times this ratio here. And this ratio, and that's now very unfortunate, this ratio is called a delta. That's actually quite funny. You see, we have a lot of other deltas here. We have a lot of deltas here. Now here, those deltas naturally mean a change, a discrete change. Now here, the delta, if you call this ratio the delta, it means the first derivative, the first partial derivative here of the derivative price with regard to changes in the underlying asset price S. It's also called the delta. It's unfortunate, so don't confuse it. And now the ideas that we discussed before, because the derivative f and the stock, the underlying stock S, depend on the same random shock set, they are exposed to the same shocks. So what you can do, you can buy the underlying share, and then you can write a derivative, maybe a put option, and you can do a perfect hedge. If your just buy the correct amount of the underlying stocks. The question is then, how much do you have to buy the underlying stock? Because that position moves against the position you have in the derivative. And so the two movements cancel out. So that's what we will calculate. So that we said, the volatility of the derivative is delta. I will now call this delta. It's delta times the volatility of the underlying stock. It's called the delta. It's a sensitivity of the price of the derivative to changes in the price of the underlying asset, but it's just the first derivative. It's a partial derivative. So let's write the derivative. We are the writer, so our position is actually negative of the value of the derivative. I have here the negative side because we write this derivative. Now the holder of the derivative then actually has a position F. The writer of the derivative has a position minus F. And then let's buy the underlying share. And let's just buy delta times the underlying share. Okay, let's look what happens then to the value of our portfolio. So we have written a derivative on those shares, and we bought those underlying shares, and we just bought them delta times. That's a quantity we bought. And this gives me the value of the portfolio. Now let's work with changes. So I have here a change in the value of the portfolio. So here's a delta, just means a change. Here the change, and here also the change in the underlying spot price, the change in the derivative price. And then you plug in 21 and 22. 21 gives me an expression for delta S, 22 delta F. So delta S, delta F, plug in 21 and 22. Then certain things drop out and you get this. Now the interesting thing here is the delta Z has dropped out. So random shock is no longer here, which means this return to the portfolio, here you have the value of the portfolio, here you have the return to the portfolio. This return to the portfolio is now certain. It's risk-free. So what we did here, we did a perfect hedge. We bought a certain amount of the underlying asset and we wrote here a derivative on those assets. And we did it just at the correct amounts. And so the movements now cancel out. And we get a certain return on the portfolio. It's actually not so surprising that this happens. You see, we said here, that's the volatility of the underlying share. And then the derivative has the volatility delta times. So that's a delta times the volatility of the underlying shares. So you have to buy actually delta times the underlying shares if you write a derivative. And then the movements of the two positions cancel out exactly. So the result that we get here is not so surprising. So that's a certain return. We have now a risk-free return. It's risk-free. And then actually arbitrage implies that a risk-free portfolio must yield a risk-free interest rate. So here I have the portfolio return in percent. Remember the change of the portfolio, value of the portfolio in that time period divided by pi, divided by the value of the portfolio. That gives me a percentage change. We introduced this notation in the first lecture. It's also applied, we said, for example, for inflation rate. You have the change in the price level divided by the price level. Okay, that gives me the inflation rate. So the change in the value of the portfolio measured in percent we divide this by the value of portfolio, so we get it measured 9%, should be equal to the risk-free interest rate. That's an arbitrage condition. And we can rearrange this. Let's say we just delta pi I have now here. I just did the rearranging. And now I can plug in for 23 and 24, I can plug in pi and delta pi. I have here pi and delta pi. You see I have here in 23, I have an expression for pi. In 24, I have an expression for delta pi. So substitute this in here for pi and for delta pi. And what you get is this here. And some of you may recognize this if you took a finance class. That's now the Black-Scholes differential equation. It's a differential equation. It determines the behavior of the value of the derivative over time. You see here, I have delta f divided by delta t. So you can solve this differential equation for the path of the price of the derivative security over time. So we have here the Black-Scholes differential equation. It determines the time path of the derivative security price. You see you have here df to dt in it. And then naturally, you know from solving differential equations, you need so-called endpoint conditions. In physics, engineering, maybe you call them endpoint conditions. Here in finance, they are called the boundary conditions. Yeah, okay, it's just the conditions at the beginning and at the end. Okay, that's boundary conditions. But also another word is endpoint conditions. So different derivatives that actually impose different endpoint conditions. So we will then work in the next lecture with the endpoint conditions for a call option. And then one can solve these Black-Scholes differential equations with those endpoint conditions, and one gets a very neat solution. Now, as a summary of today's lecture, so it's a Black-Scholes model. Options are valued by constructing a risk-free portfolio. It's actually called a delta hedge. And then it's argued that this risk-free portfolio should yield you the risk-free interest rate. It's called the delta hedge because we write here a derivative, maybe a put option, and then we buy the underlying asset delta times. So that's a quantity of it by. So this sensitivity or this first derivative here is actually called the delta. And we speak here of the delta hedge. The delta hedge produces a secure return. The portfolio then actually becomes risk-free. So that's what hedge funds should do. So you see they write options, and then they buy the underlying asset to hedge. And if they do a delta hedge, then okay, then it looks quite fine. But quite often they don't do delta hedges, and they have open positions, and then they are troubled in a financial crisis. Anyway, the delta hedge, there is something additional that we have to consider. This delta is not constant over time, but this also we will see in the next lecture. Okay, so that was it for today. We have the Black-Scholes differential equation. We derived that one rigorously, and then okay, we say up to now we say we have to solve this differential equation just with different endpoint conditions for different types of derivatives. Okay, thank you. That's it for today.